Ladies and gentlemen, welcome to this webinar in FEM Design 19. Today we're going to look at a reinforced concrete plate. We're going to look at the design workflow in FEM Design for a concrete plate. We're going to go through it. We're going to take a look at the structure, go through the loads and analysis and see what kind of results we can get in a plate. And then we're going to look at the concrete reinforcement design. My name is Flavio. I will be the presenter today. I am joined by my two colleagues, Ciprian Țiba from Romania and Siavash Ehsan Zamir from Sweden. They will help me with questions that you might have. Hopefully you will. We are using GoToWebinar for this presentation today. Please, during my presentation, if you have any questions, type them in the questions field. You have questions field here in the window, and Ciprian and Siavash will help me and answer these questions for you, and you will get the answers. We are quite a few today, so let's see how many questions we get. Hopefully we will be able to go through all of them. Also, of course, if we have any extra questions afterwards that we did not manage to answer, we will get back to you in an email with everything. Okay. But let's get to it. Let's get to it. We will take a look at two models today. The first model is a concrete plate, which I have modeled in FEM Design. It is supported by some columns, by some walls, and of course, which in turn are supported by some supports. We have a step-by-step training on how to model in FEM Design. Of course, if you are new to FEM Design, completely new, as in this is the first time you see this program, I would recommend you apply for a trial, first of all, on our website and get a trial version so you can test it for yourself and also get some training and get started with the program. Today, I have already made the model, so we don't use any time on showing how to define geometry and the columns and everything. So we have it already made. I have some loads as well applied on the structure. I have self-weight, which is actually applied automatically in FEM Design. So the load combinations. I have my load cases here. Dead load, pro-structural dead load, live load. The dead load is applied automatically if I select the pro-structural dead load and live load ordinary. Just a second, I need to check that everything is working. Especially the audio, which is pretty important. It looks as you should be able to hear me. Great. I saw yes here. Someone answered. Perfect. Great. Appreciate the feedback. All right. That's the most important part, that you can hear me. Pretty important. So I have some loads. I have load combinations. I've made some ultimate limit states combination, ULS, and some serviceability load combination. In FEM design, it is possible to generate also combinations automatically. I'll not go into that, but just so you know, if you have a lot of load cases, you can group them in load groups and generate load combinations automatically. These ones I've made manually. Here it's possible to define all sorts of loads. We are focusing right now on gravity loads and see how the plate behaves under those loads. In the Finite Elements tab, we see the mesh, which is a default mesh generated automatically by the program. What I have also in the Finite Element mesh is the peak smoothing. Some of you may have used it before. Peak smoothing now has two options in FEM design. You can use a higher order shape function or a constant shape function. Of course, it is up to you how you decide on which method of peak smoothing you wish to use. It's basically higher order shape functions. You can use it, or I say I use it when I'm dealing with crack section analysis, the higher order shape function, because the reason for this is because it can handle local stress increase and local stresses. And this constant shape function used when you just make a regular bending moment check. Again, it is up to you on how you decide to use it. Some of you might know this already, some of you not, which is perfect. You will learn about it today. Hopefully, you will learn a lot of things today. But I have applied some peak smoothing. Next, I've already run the analysis. I'm just going to run it again. And in the quick tools window here, I have all my results after my analysis, which I can see. I have displacement, which I'm going to look at today. I have activated a global maximum minimum result for all my visible objects, so I will get the maximum deflection for my structure. I see here I have approximately 5.5 millimeters. I can adjust the number of digits, decimals that I want to show. Of course, I have my reactions. Here is the general view for my reactions. I can see the point reactions under my columns. I do have several of them, but of course, they're negligible in my case. I only have vertical ones, so I can see also some forces underneath them. In case of my line supports, of course, these point reactions are in kilonewton. Then I have some line reaction in kilonewton per meter, sorry. And I have some resultants as well. Of course, I can customize this reaction display. I can, I see here all my components for my line. And I can choose the forces and the directions that I want to show. I don't have any surface. And for the resultants as well. Let's say I turn off the moment. So I can only see the resultant here in kilonewton. See if I can get a value for it. So you have a lot of options to display your reactions as well. What I want to see now is some more results here in the results tab. Again, if you have questions, please type them in the question section in the questions in the questions tab. Okay, great. Let's look at shell internal forces. I can see the moment. Mx is the moment in my shell. You can see it like this, which is along the x-axis. Mx is along the x-axis. And I see basically my plate as supported by columns and these walls. And I have the moment diagram as a graph. Of course, I can display it as a color palette. I do have the maximum minimum result turned on, so I can see the maximum minimum value. I can see the my as well in the y direction. I can see the stresses in the plate as well. I'm not going to go into this now, but all these results, of course, are here. Sigma x, y, and then tau, sigma von Mies. And all of these results are available basically from this analysis engine, which is comprised of the 3D structure program, in which you define the structure, apply loads, define a finite element mesh, and run an analysis after you get the results, forces and displacements. This is basically the analysis module. Then you have the design modules. You have foundation, reinforced concrete, steel, and timber. Of course, today we're going to look at the RC design tab. This model is, I'm going to use this model to show the workflow. So I have my structure, I had my loads, I ran the analysis and I got results. Now I want to see my design reinforcement, my reinforcement in the plate. Well, I can use auto design and I can use manual design in FEM design. For this example, I will use the auto design just because I want to go through the process and see as many tools as possible. After this, I will have a different model with a more specific set of problems, which we will take a look at in more closely to how we can design the reinforcement in a plate. But for this, I just have my plate right now, and I see the tools here. What is really important is design calculation parameters, where I can actually see my calculation parameters. These calculation parameters are used to calculate minimum reinforcement and initial required reinforcement. I need to set a position for my reinforcement so the forces will be applied in that position. It is also where I set the allowed crack width and apply minimum reinforcement. Again, we will go back to this. Well, this is where I set my calculation parameters. Let's go back to a 3D view. Okay. Then I have the check tab where I can actually perform a quick check on my plate I do get the warning that reinforcement is necessary. This is because I don't have any reinforcement yet. I just set some calculation parameters. But I do get some very important results, which are the required reinforcement. This is the X bottom required reinforcement. This is the millimeter square per meter amount of reinforcement that I need to put X in the X direction bottom. Of course, this is the maximum value, 585. I have a whole color palette here, which shows me the different reinforcements which I need. And I can click on it and see what kind of reinforcement I have. I can see here with the blue, I have very small values here, close to 0. But this is the required reinforcement, which actually gives me an idea of how much reinforcement I need to put. Of course, I have Y bottom as well. Top reinforcement with the concentration in the columns and Y top. So again, you have different tools to apply reinforcement in FEM design. For this example right here, I'm going to use the auto design. Go to parameters here. And here is where I set my parameters for base net and additional reinforcement. The base net will be applied all over my surface, and additional reinforcement will be applied where there are extra reinforcement required. Also for the top face as well. Again, I'm just going to use this default one, click design, and surprise, this plate is very good. Bottom reinforcement, X direction, bottom reinforcement Y, top X, top Y, and I see the utilization here in the bottom. So everything is below 100%, which means everything checks. I also have a crack width utilization here, which is 34%. I have applied reinforcement according to the auto design, and everything works. Everything is fine. What I can do is have a detailed result report. So if I go to this magnifying glass, I can select my plate and I can check. I can click on a point on the plate and see a detailed calculation and report of the design forces used to calculate the reinforcement, a diagram of the stress distribution, minimum reinforcement calculation, see a table here, and the required reinforcement calculation. I can do this for any point on the plate. I can save these points as well and then go back to them. So this is something that I can do in FEM design, get a detailed calculation report of my plate. Just gonna do another check up here. See that everybody's still with me. Okay. So what I have now is I've made a load combination calculation in FEM design. I have made a deflection calculation, saw my deflection, added some reinforcement. I can also see the cracks now. Let's see. I don't have any in the bottom. I have some in the top. Oh, 0.14. Hence that utilization of 30% for the crack width. In the RC Design tab, I also have the possibility to do punching reinforcement. Let's take a look at this real quick. I'm not going to spend too much time on it, but it's good to know that automatically you have some punching zones and where the columns meets the plate. And real quickly, I'm going to select all of them and perform a check. You can see the utilization afterwards. And of course, the color scheme of the utilization. I do have some okay results here with yellow. I have a red one here. Again, I'm going to use the auto design. You can also use the manual design really and select these types of reinforcement display. I'm just going to use this auto design. Here is some stud rails from Payco as well as a type of reinforcement. I can set my parameters here. I also have these types of punching reinforcement. I'll just use this one. And then I click design and I'll get a warning which says that the stud reinforcement exceeds the limit. There's some, of course, some verifications that I need to be aware of. I don't want to use too much time to figure out this. So I just want to use something that works for now. Of course, I need to pay attention to all the warnings and distances to make sure that I respect everything according to Eurocode. But I also have the detailed calculation here for this, and I get a reinforcement utilization and the bars here for this type of punching reinforcement, the compression resistance, shear calculation resistance, and a detailed report here, a calculation report here. So that's something that you can do. Something very nice that FEM design offers is the punching reinforcement design, where you can, on the same model, put punching reinforcement as well and design it for that. Okay. Now I have some reinforcement in my plate. I can go back to my analysis and I can perform a crack section analysis. This crack section analysis takes into account the reinforcement in the concrete. I can do this by going to Analysis Calculations, set up by load combinations, and select the crack section analysis that I want. Here I just tick the box, click OK. And now, through an iterative process, the plate will be calculated, taking into account cracks and stiffness reduction into those cracks and the reinforcement. So there is a new stiffness calculation for the plate, taking into account the cracks. I can see my deflection. Maybe it's not that much of a difference, but for the deflection. But let's go to the RC design. Check the crack width now. Nothing in the bottom. Oh yeah, I have to make another check, of course, for the plate. Still have some cracks. It looks like they're a little bit less cracks in the top. At the bottom, nothing. Of course, I can increase this. I can increase the load. Also, my concrete has a tensile tension resistance for the concrete, which is taken into account in the material. So I can actually go back and set that resistance to 0 so I can get some cracks. But if I want to do a crack section analysis with concrete, with the reinforcement taken into account, I can do it like this. In the material, I can also set some long-term parameters, which are creep and shrinkage. So I go back to the structure, and in the material here, in my case, C30 by 37, I have the option to enter some creep coefficient for my different load combinations and shrinkage. Again, this is up to you how much you put here. We also have a shrinkage calculator. Let's see if I can find it here. Probably would have been nice to have it from the beginning. Just bear with me. Here it is. This is the concrete creep and shrinkage calculator. It is a free access on the internet. So you just set your parameters here, click calculate, and then you will get a creep and shrinkage, which you can use in your calculation. So you can make it here, and then, of course, one way to do it is this, and then put it back in the model. What was it, 1.6? And this is the material property, so it's taken into account along the calculation with the material, so just so you're aware of that. Let's just make a calculation now. So you can study the long-term effects for your plate. I see a question here was about the shear capacity. I'm sure Siavash and Ciprian will get to that. But that is the shear capacity, which is calculated. So let's take a look at my deflection, for example, now. because that's what I want to see when I do the long-term effects. But I do want to see it for serviceability limit states, because that's where I put my shrinkage and creep. It is 8.8 millimeters now, so it's higher. I'm sure it was lower before. Because we only looked at the ULS. That was my bad. But this is for the SLS long-term effect. That's what I want. That's what I set up my creep and shrinkage coefficient for. So this is basically a long-term study with taking into account creep and shrinkage into my structure. This is what I wanted to use this model for. All right. It's already half an hour in, so let's jump to the second model that I have prepared, which is again not too much of a complex model, but we'll see how we could create a realistic reinforcement design for this kind of plate. I see here it's a flat slab supported by some columns. Let's see, I have some loads again, load combination. Nothing too complicated. Then I have this peak smoothing function, which of course works best if I do have a smoother mesh. I can either make a smoothing of the mesh around the column edges, but this is a small model, so I'll actually make it from here. I'll set it to 0.4. So there, it's a little bit finer. So let's go straight to the RC design tab here. I can do the same calculation here. I can just go to design calculation and check. I'll go to load combinations. Let's look at the shell internal forces mx. Let's look at it with this graph. So this is actually peak smoothing working as a higher order shape. This is what I have set. Again, it's up to you what kind of peak smoothing you use. I can have it, the other way to have it is the constant shape. Let's see. Let's use it for mx, my, just to see the difference. For the shear force, always use higher order shape function for the shear force, higher order shape function. I'll just set it like this, redo it. Let's see if I can see the difference. Probably could have made the mesh a little bit more finer, a little bit more fine. Oh, not here. Let's see if this is relevant, if we can see a difference. Yeah, we can see a bit of difference. The here is actually pretty good. It's the difference between constant shape and higher order shape. Again, it's up to you how you use it. I use higher order shape when calculating crack section analysis. I use constant shape function when simply calculating the bending moment and making a check for that. You have both options available. Okay, let's go through the RC design. Again, okay, let me just hide these results. I have the calculation parameters, which I can set here in the beginning. As I said before, here is where the minimum reinforcement is calculated. Here's where you set the crack width and apply minimum reinforcement where it is relevant or not. Let's keep it on for now. Okay, I've only set the calculation parameters. I have no reinforcement yet. Let's do a check. Of course, I don't have any reinforcement yet, so I don't get any utilization. But again, I get the required reinforcement. This is a very, very important result for me. The required reinforcement is basically how I design my reinforcement for the plate. Again, I get these areas of coloring using the color code, the color palette, and I can see this 175 millimeters per square meter millimeter square per meter, which is basically the minimum reinforcement. So right now, I would need here a reinforcement net of 175. That's the minimum one. But if I go here to calculation parameters, this is due to the fact that even the smallest stresses in this plate will activate the minimum reinforcement. So that's why I get this minimum reinforcement, even though I might not use it. I might not need it. Let's deactivate this for a second and see what happens now. I actually get 0. I get 0 necessary reinforcement in the X direction, of course, right now. That's just bear in mind that I'm at the X direction bottom. Let's look at the Y direction bottom. Again, the same. I have 0 values here. So this is, I actually don't need any reinforcement here in X or Y bottom. This is what the required reinforcement tells me. I only need reinforcement here. This is areas where I actually need reinforcement, 455. And again, this is up to the engineer. This is up to you how you want to reinforcement. It depends on your method. Maybe you actually want a base net all over the plate, which is fine. You can have it. But some people might not want to put reinforcement where they don't need to. You want to optimize this layout and save on reinforcement. So you can do it like this. You can actually have reinforcement here where the values are highest. Let's look at the top for a second. Let's put the minimum reinforcement back. Let's look at the top. At the top, I have actually reinforcement necessary in the column where the column meets the plate, of course, and in the other direction. Let's do a auto design now with what I have. Let's just say I designed it. What I get is, okay, let's see it in a better way so it's more clear. I get this phi 20 by 150 all over my plate. That's not good. I don't want that. To have a base net for the top reinforcement all over the slab, where in reality I only need actually that much of reinforcement here in the column area. So I have to make sure I use the base net for the top face. So I set this base net. Let's take a look again at the minimum reinforcement which I need, which is like 226. Of course, this is 0 here. 175 actually, lowest. So let me set my parameters here. I'll use a base net. Let's use 8. I can even use 250. Okay, let's design it now. Okay, so I do have a base net which is 201 millimeters, which covers the whole plate, and then I have the additional reinforcement of, okay, this is, let's hide this result. Then I have the area where I actually need extra reinforcement here. Again, how I set up my parameters is the key to how I use this auto design. In the end, this auto design is taking into account numbers and your parameters. The required reinforcement is the one who tells you what kind of reinforcement you need. So then yet again, it's up to you how to use it. You have the manual design here, which allows you to have put the reinforcement where you actually need it. Let's see. There's one more tool which you can have. Let's see if I have it. I don't know if you used this before, but you can have this shape set to here. Let's see if this does anything for the auto design. Let's see it now. Not much. But again, it's because of my parameters how are defined. Let's take a look at the bottom. Yeah, I actually get a base net, and that's it, around the whole plate, which is, it might be fine. I don't know, but that's what I set. That's what I said. Let me see if I can make this. Was it 175 the minimum reinforcement? Okay. Let's try to use this as well. Delete this, which will avoid some areas. Yeah, this is the kind of reinforcement I deal with. I can again, I'm using auto design, but you can optimize it with your manual design tool, and of course set the parameters accordingly. We are 45 minutes in. We have like quarter of an hour to go. I hope this was useful and you found out some new tools. This is what I had in mind to show you. Now I have Siavash here, which I am going to check with and see if he has anything to add. Siavash, do you have anything to add? I can also give access to your microphone. I think you can do that by yourself too.
Yes. Okay, so regarding, I was actually speaking to one of my colleagues in the meantime. So was there any question, or do you want me to just summarize something new?
I can hear you now.
Yeah. Can you still hear? Can you hear me?
Yes. Do you have anything to add?
Regarding this, like I know that we do get a lot of questions about how FEM design actually applies reinforcement, and that there is that a lot of people say that it puts too much reinforcement everywhere. And we should also remember that even when we have small stresses, we actually the program will automatically try to put reinforcement according to the minimum reinforcement. So it might be good to turn off the minimum reinforcement and then turn on the reinforcement, and you can play a lot with the reinforcement to get a very good answer. But if you don't want to do that, I always recommend that the best solution is just to check the required reinforcement, and you don't have to apply reinforcement manually. It's very good to apply reinforcement manually when you need to have how much reinforcement there is, so that you know the quantity. But other than that, when I'm using these functions myself, I usually just check required reinforcement, and then I manually put reinforcement in a drawing software. So I don't add the reinforcement myself, or a lot of times I don't use automatically added reinforcement by the software either, because it's very easy to check the required reinforcement.
Yes. Actually, now I deactivated the minimum reinforcement, so I can see that the additional reinforcement is only like this. Of course, not optimum yet, but yes. But Siavash said as well, and stressed this, that you have this option to use minimum reinforcement where it is relevant or not. Other way, you can control where you have reinforcement and control what FEM design puts in.
And I can also add, can you hear me, by the way?
Yes.
Yeah, perfect. I can also add that the best, another good solution is that when you add these reinforcements, so that you change the parameters for how the reinforcement should be assigned by the software. One recommendation a lot of times is to actually, as a base net, put the you can show that there. So in the base net over there, it's very good to put the reinforcement equal to the minimum reinforcement. That way you can save a lot of reinforcement, because then additional reinforcement will try to put extra reinforcement where it's actually needed by the forces. So that's a good way. of doing that. So trying to check how much do you need as a minimum reinforcement, you can do that in detailed results, or you can just check in required reinforcement which kind of reinforcement that is repeated a lot of times. Then you will know that that's the minimum reinforcement. And in the top phase, if you can switch to the top phase there, yeah, perfect. So in the top phase, sometimes when I have these very, very small stresses and the program wants to put these minimum reinforcements everywhere, then I usually put a very small value there. Like I usually put like diameters of 6 or 4, and I put very high, like 300, so that's even more than that, so that I have like an area equal to approximately 40 or 50 square millimeters. And by doing that, I put a reinforcement that pretty much can be neglected during calculation, and I will get only reinforcement in the areas where I actually have forces that are not too small to care about.
Which is the additional reinforcement.
Yes.
Okay. Okay. All right. Thanks, Yavash. Okay. Well, we've looked at this design tool and FEM design, reinforcement design tool. We've heard some good tips on how to use it. Yes, the section is still not okay, but the point was not to make the section okay here. It was just to show you some tools to design it and how to apply the reinforcement. Yes, the shear capacity is taken into account, but not designed for. So the reinforcement is not designed. It's not applied. It just gives you an area that is necessary.
Can I answer to that question, Flavio?
Yeah, Ciprian, sure.
So about the shear capacity, there were a lot of questions related to it. Usually in a plate, which is 8 centimeters, let's say, thick, you do not place any stirrups, right? So this was made just as a pure example. It wasn't considered, as Flavio said, for shear verification. It was just applied a theoretical load. Basically, when you face that in a real project, you just increase the thickness because, yeah, you don't place stirrups in very small thickness plates. That is one thing. And another thing is that the punching shear reinforcement, that's something different. So, yeah, it was made as an educational example. It's not a real life project. But as I said, if you face that in a real life project, you just increase the thickness of your plate. Yeah, thank you.
You can't get the shear capacity as in utilization here. It's not okay. Let's see, that's a good question, actually.
If you look to sigma tau, you can get the values.
Yeah. Can I get the utilization of this shear capacity? I can get the required reinforcement. for shear capacity, and yeah, I can get that tau. Yeah, this is for the stresses. No, in necessary or in required reinforcement, you get it as. I guess it depends on each case.
Maybe I can add an answer to a question. One of the question is regarding internal forces that are linked to the local axis. So the question was that are the internal forces that we get for the local coordinates? And the answer for that is that yes, the results that are in analysis. So all results that are in analysis, we have to differentiate between analysis results and design results. Like for example, if we would take bending for an example, if we would go up to the MX result, for example in the shell, yeah, we could go up to the load combination and then we can choose shell internal forces MX. So this big M means that this is an analysis result, and X prime you can see, and then that's according to the local coordinates. But we also have another result which with small m, which is called the design result. So then when we go further down, we have something called design forces. So the difference between these are, of course, that the MX, which is a bending moment, for it, when you design the reinforcement according to Eurocode, you have to add an in-plane torsion bending moment, or you have to add it with MXY. So for example, when you have big MX, you have to add it together with a big MXY, and then you get the design forces. These design forces, as you see, they have small m, and they are not according to the same coordinates actually. And the reason for that is that the analysis results are according to the shell, the local coordinates of the shell, while the design results are according to the reinforcement coordinates. Now, usually they are the same. They are designed to be the same so that you can check the results, but they are actually not. You have to remember that I've seen some results where you have rotated a shell element and then they do not align and the results are different. So one way to show them that is the reinforcement results is actually if you check the calculation parameters, right? Yeah, I think you can just turn on the calculation parameters there. So here you can see that if you zoom in, you can see an X direction, and that is the local coordinates you can see for the reinforcement. So, and since that X coordinate is actually the same coordinate or will be aligned together with the shell local coordinates, so a lot of times you will get the same result, but sometimes that is not the case, and you have to think about it.
Mm-hmm.
But maybe we could also show that, like, is it possible to turn on, could you turn on the local coordinates of the shell so that the users can see how they view the local coordinates of the shell? So yeah, they're in the graphical
system.
option. Exactly. And then okay. Perfect.
It's this one.
So you can see exactly it's that one. So you can see that that is the x direction, and that x direction, the green arrow is aligned with the x direction in the reinforcement down there. So you can see that they are usually aligned, and it's for the it's designed that way. But sometimes if they are not the same, when you're rotating a shell element and when you change the direction, then you will see that the result might confuse you. But you have to consider that it's two different coordinates.
How are we doing with the questions? I think we covered them. I think if we need to answer any more, we can send an email afterwards with the answers. But other than that, thank you very much, everyone, for joining. Remember, if you're using FEM Design, perfect. If not, go to strusoft.com. Let me see if I get that already here. strusoft.com. To apply for a trial, go to FEM Design and get started now. Here you can apply for trial license and fill out this form. Okay. That's all from us. Thank you also Ciprian and Siavash one more time for helping and attending and hosting this webinar. Everybody have a nice day. Thank you.